Welcome back, everybody. Continuing Chapter 9 notes on potential energy and conservative forces and conservative work. And we've just talked about how gravity is a conservative force, that it does kind of conservative work. That is, if you do work against gravity, then now gravity is now ready to do work for you, and you get all that energy back. Well, the same thing is true of springs. Springs are conservative force items, for lack of a better term. They for any force or any work that you do against the spring, it's now ready to give it back to you. This may be a familiar equation from the last chapter. Work done by a spring is 1/2 kx squared. All right. And so where do we get that from? Well, that work is force times distance, right? And so the force of a spring, let me see if I can do this. Force of the spring is really the spring constant K times x. All right, and if you displace that force some distance x right there, that's kx squared. All right, it's kx squared. Well, where does the 1/2 come from? Well, if we let me see if I can shrink this down a little bit. Well, you remember that if we plot force, there we go, which is k. Can't even write. Force, which is kx, versus distance x on the x-axis right here. Well, if you don't displace a spring, it's not going to feed back with any force. So you start with 0, but the more you displace it, the more you displace this x right here, the more it feeds back with more force, and so it's kind of like an increasing force the more you squish it down. So let's say you displace it, I don't know, this much right here. Okay, you've got your x on the x-axis, you've got your kx on the y-axis right here. So we really have a triangle that is creating a shaded area. Right, and the work done by that spring is that shaded area. Work done by the spring right there. How do you find the area of a triangle? Well, it's 1/2 base times height, right? 1/2 x is the base, and the height is kx, or that is the force by the spring. So that's where our 1/2 kx squared comes from. All right, and we can think of this as a conservative force, that is, springs doing conservative work, because as you take a spring that, say, has no compression right here, here's a spring, all right, it's at equilibrium, it's not compressed or it's not displaced at all. And if you squeeze it down, if you compress it, you displace it some distance, you are putting some potential energy into it. Right? You're ready for it to do work for you, and so it will give that work back depending on however much you displaced it right here. All right, so we can potential energy in a spring. Sorry about that for that little slide popping up. The potential energy in a spring is 1/2 kx squared. All right, it's the amount of work that it's ready to do. All right, and if all that, so say we have a squished spring right here, all right, if that spring is now able to return to its original position, then all the potential energy in the spring here is going to mean that it's going to do some work done by the spring. It's going to release that energy in the form of work, whether it's pushing a block along a track or whatever the case may be. So the work that the spring is able to do is really a function of the potential energy that it has. The potential energy that it has is really the same thing as the work that it can do as described in the last chapter. That is 1/2 kx squared. All right, let's just do an example that kind of illustrates that, and I think you'll be all ready for these kinds. This really isn't all that difficult. Let's see here. I'm going to move this up a little bit. We have, in fact, the hardest part of this problem is the fact that it requires some conversions and the fact that we need to find out what the spring constant actually is. All right. First of all, we have the spring being compressed in centimeters. Well, we don't like that. We like meters. So let's turn these centimeters into meters. So 2.25 centimeters. What do we do to convert it to meters? We've got to move the decimal point 2 places to the left, right? So that's 0.0. It's not a very good decimal point, is it? 0.0225 meters. Okay, and The question is, what's the potential energy when it's compressed 3.50 centimeters? Well, let's change that to 0.0350 meters. All right, that's going to make our lives a little bit easier right there. All right, so it's telling us that if we displace it a certain distance, it feeds back with a certain force. All right, so what does that tell us? Well, that tells us the spring constant. The spring constant, K, or you might say the springiness of the spring, that's a measure of the spring's, like I said, springiness in newtons per meter. Right? For every meter you displace it, it feeds back with a certain number of newtons. All right, well, how many newtons to how many meters? We're told that it's 120 newtons if you stretch it 0.0225 meters. 0.0225 meters. All right? So, if we do our math right there and simplify that, we should be able to turn that into newtons per meter instead of newtons per 0.225 meters. 120 divided by 0.0225, I get 5,333 newtons per meter, which must be a pretty tough spring. That's a lot of newtons if you stretch a meter. Of course, a meter is quite a long distance too. Have you ever really stretched a spring, a meter? So it seems like a lot, but maybe it isn't. But that's our spring constant, 5,333 newtons per meter. All right, so the question is, what is the potential energy of the spring? We just put our energies, oops, I don't want a regular box that, I want to just dotted line box it. We just put our brain power into figuring out the spring constant. Let's find out the potential energy in the spring. And this is going to be the easy part. We know the potential energy in a spring is, let's see here, potential energy in a spring is 1/2 kx squared. All right, so 1/2, what's our k? K is 5,333 newtons per meter. And our x, that is how much is it being displaced? Well, it's being displaced 0.0350 meters. All right, so we use the original force and the original displacement to find the spring constant. Now we're using the spring constant and our equation for the potential energy of a spring to find out what the energy it actually has. So it is 0.0350 meters, and we're going to square that value, right? Because that's part of our equation right there. So what do we get? 5,333 times 0.035 squared times 1/2. That gives me 3.26 joules of energy. All right, potential energy in the spring right there. And that's what I get. Why won't this write? There we go. And that's our answer. All right, it's really just a practical application of our potential energy of a spring equation, 1/2 kx squared, which is very, very much like the work done by a spring. So now that this energy, the potential energy, is in the spring, it can now do up to 3.26 joules of work, whether it's pushing a cart across a track or whatever the case may be. So that's example 9.5, a practical application of our potential energy in springs equation, and you should be okay to do the next homework set, which is on potential energy in springs. So if you have any questions on this or on those problems, make sure you come see me. But in the meantime, thanks for watching, and I'll see you on the next one.